understand rotational work and power. Suppose this is a fixed axis and this rigid body is free to rotate about this axis, and a force F is applied onto this body. This force has two components. One is tangential, the other is radial force. This radial force, then obviously it is passing through the axis itself. As a result, this radial component will not be responsible for doing any rotational motion of this body. It is only the tangential force which will do some work. As a result, it can have alpha about this axis, that is, it can have angular acceleration about this axis. Now, if we are interested in finding the work, then obviously we know through our understanding what we understood in our lecture in work, power and energy, that is, work is F dot S. Similarly over here, if we look over here, that this is a tangential force, this tangential force is applied over here, and as a result there is a very small displacement. If this is R, this is d theta, so this length, which is almost a straight line, it is r d theta. This is circle in which it is moving, force is applied, that is, which are talking about this tangential force. And if we look from here, this is displacement is r d theta, almost a straight line, infinitely small displacement r d theta. So work of this force is going to be Ft into r d theta, that is, work rotation Ft into r d theta. It is only the tangential force will work. The radial force, normal force, this will do no work because this is passing through the axis itself. As a result, its torque or its rotational effect will be zero. So the small work which is done is tangential force into r d theta. Now this force and distance F into r, we know force into perpendicular distance between line of force and acceleration. That is what is R is. Force is tangential and this is R about this axis is R only at an angle of 90 degree. So torque of this force about this axis is force into perpendicular distance between line of force and axis of rotation. So Ft into R, that is, we can put it as torque. So torque into d theta. So for finite angular displacement, the total work we can get it from integrating both the sides. So work rotation comes out to be torque dot d theta. Theta goes from theta 1 to theta 2. Now if we are interested in instantaneous power is a rate of doing work, that is dw by dt. So it is dw by dt. dw is what? It is torque into d theta by dt. d theta by dt is equal to omega, angular velocity. So this comes out to be torque into angular velocity. As we did in our work per energy, that is kind of, you can say, that is linear power. It was force dot velocity. Over here, force analogous to force is over here is torque, and analogous to linear velocity over here is angular velocity. So power comes out to be, instantaneous power comes out to be torque dot dw. So remember that this is the instantaneous power. Otherwise, the average power is the total work done divided by total time taken. Now if we talk about what is analogous of work energy theorem, what we did in work power energy, where we had been dealing with the motions as the linear motions, over here in rotational mechanics, the analogous to that theorem is, that is, the work of rotational is change in kinetic energy, that is rotational kinetic energy. That is rotational kinetic energy final minus rotational kinetic energy initial. Rotational energy is obviously half I omega square. So half I omega final square minus half I omega initial square. Over here, that's what we are talking about is, that is when we have a fixed axis, and about this we are applying a force. This force has two components, one is tangential, the other is radial. Only the tangential force will be responsible for doing the work, not the radial force, because that is passing from the axis of rotation itself. So as in linear mechanics, the force was doing some work, over here torque is doing some work, and it is changing the rotational kinetic energy about this fixed axis. Let's take an example.